can see here. Yes. Can you see it? Is it fine?
Yes, yes. Can you put it on full screen, please? And
yeah. Yes. Is it fine?
it's still, yes, now it's fine. Okay, good.
Okay, so it works.
Thank you very much, and please go ahead.
Yeah, thank you. I'm so proud to present our new results today. And thanks for Johan to organize this meeting and let me to meet so many researchers. My background is not a mathematician. I'm working with the trees. I'm working with trees to understand how the trees respond to climate change and about the tree physiology, work with the dendral ecology, and work with wood science. But then when I started to collaborate with Peijian and Johan, I found that the geometry and the mathematician is very interesting. So then we started to work something with the geometry. And today I will give you a presentation about the geometry of tree rings and from 6 issues. So then this is a tree and it's a trunk. And we say it's a window in a tree to receive and achieve environmental signals. So in the beginning, I think many years ago, from a dendrochronologist, we are more think about the tree disc is like a circle. But every year for the conifer species, they are form one tree ring. When they are forming these tree rings, they are affected by the environment, like the precipitations, like the slope, and also like the temperature, and also like the wind speed, and also the wind direction. So this kind of environment signals, they will influence the tree ring growth. The first parameter is about the ring width. So we see here, this is the tree rings. So it has the width, but then many years, we are working with the tree ring width. How is the precipitation and how is the temperature fluctuations and how is the soil water content changes, the tree ring width. But we are not thinking so much about the tree ring shape. What has happened? And 20 years ago, they have researchers in Europe started to work with the tree ring shapes, but not so many. And so we see here, this is the disc, and this is a cedar spruce disc. So I see this is a piece, and this is a bark. So for trees, they start to grow from the piece to bark, and every year it will form one ring. For the light color part, this is ironwood, and for the dark color part, this is the natewood. So we see this is a tree ring shape, and we call this one as a tree ring boundary. And we ask question whether it is like a circle or whether it's more like an ellipse or whether it's a superellipse. So then normally we'll try to calculate the area within the boundary of each other rings. So if we try to use a circle and we use this function, if we take it as an ellipse and we use this function, if you think about the superellipse and we use this function to calculate its area within the other rings. But for dendrochronologists, we are mainly using the circle function or use the ellipse functions for many years. And then for the basal area increment, this is very important parameters for the dendrochronologists to use to calculate how is the forest production, how is the volume of the tree trunk in a forest. So we can see for here, this looks like a tree ring disc. So we see for the N, that means the tree rings formed in the current year. If it's N-1, that is a tree ring formed in the previous year. Because the tree formed the tree rings from the piece to the bark. So if we use the circle equation to calculate the basal area increment, so this is the function what we used. And if we think about the tree ring shape, it's like an ellipse. So we use the ellipse function to calculate the basal area increment. And if we use the superellipse, then this is the function what we can be used to calculate the basal area increment. And for the A, that is a major semi-axis, And for the K, that is the minor semi-axis divided by the major semi-axis. So for the superellipse equation, I think all of us are very familiar about it. Is Namu introduced a generalized version of the ellipse equation, which was referred to as a Namu curve or the superellipse equation. So I see this is the function what is like. It's very simple, but it can fit for so many different types of geometric shapes like the picture shows. And for the alpha and the beta, they are the major and minor semi-axis of the superellipse. And n is an arbitrary positive number. So I see with the n changes from almost close to 0 to 0.5 to 1 to 1.5, they are changing the shapes. So I see when the n is between 0 to 1, the superellipse looks like a four-armed star. We can see with the concave sides. And if n equal to 1, so the curve is like a robot with corners. If the n is between 1 to 2, so the curve looks like robot with the same corners, but with the convex. If the n is bigger than 2, so we see the curve looks like a rectangle with the rounded corners. So we try to use a superellipse equation to fit the trimming shape. And here we show the process of extracting the coordinates of the trimming boundaries. For the step 1, the outer boundary of each tree ring, we see this is like the boundary of the tree ring was manually redrawn using Photoshop. And for the error computation, the interspace inside redrawn tree ring boundaries was filled with the black, and the tree images were then cropped and converted into black and white BMP images. So then it looks like this. So we extracted for all the tree rings from one disk for different species. And for the boundary coordinate data of each tree rings were extracted using the MATLAB according to our collaborator, Pei Jianshi, has programmed it in MATLAB. And for the number of approximately equidistant data points from each tree ring parameter was fixed at 600. So we see for each tree ring shape, we are around taking 600 points for it, and we try to get this running in our software. And this is the results. So we see for this picture, this is 6 different species. We have Douglas fir, Japanese notch, silver fir, Norway spruce, Sigar spruce, and we see this is the original pictures of the tree ring disc. And this is the fitted tree rings for these 6 different species. And what we found, we can see for this is a piece, but you can see as the tree grows, its geometric center has been changed and will be moved. We call it is eccentric. But it doesn't influence for superellipse functions to fit with the trimming shape. And then let's go to see some results. So for here, we use this adjusted root mean square errors to calculate and to see and whether this superellipse functions can fit the trimming shapes very good. So for here, we can see A represents the observed arrow, so that is the real arrow. And then the N represents the number of data points. It's around 600 points for one trimming shape. And then the RSS is the residual sum of squares between the observed and the predicted polar radii. So for here, we can see this is 6 tree rings, and we randomly select one tree ring from one disk. Like we select 14 tree rings, number 14. For Douglas fir, we choose 22 to grand fir, and we choose 28 to silver fir, and 17 for Sigar spruce, and 26 for Japanese notch, and 12 for Norway spruce. For the green curve, it shows the actual tree boundaries. This is what we redraw it. And then the red curve is the superellipse equation fitted to the boundaries of the other rings. So let's see the adjusted root mean square arrows, so I can see the superellipse function fit the trimming curve very good for the 6 different conifer species. And then we plotted the parameters, read the values of the parameters from the function. And the A value, that is the major semi-axis. So you can see for GF, for x-axis, it shows the different species. So for the GF, that is a grand fir, so we can see it has a higher value of A. So that means the discus is bigger than the other 5 different conifer species. And for the K value, it's equal to the minor semi-axis divided by the major semi-axis. So we can see they are lower than 1. So from here, we can see they are not really like a circle, but it's more close to an ellipse. Especially for the GL, for the Japanese notch. So we can see its K value is close to 0.9. For here, each point is represent 1 trillions, and it's around 40 to 45 trillions for 1 disk. And for here, why we can compare for the different species is because we are using the disk from the common garden experiment. And for all the trees, they were grown in the same year, in the winter of 1963. That means they have the same age. So then there will be no age effect. Normally, when there is age effect, they are significantly influence the tree increment rate. And for here, let's see value. So we can see for the N value, it's for its average value is close to 2, but it changes, it has the fluctuations between the tree rings from year to another year. So this is for 1 disk for Douglas fir. So I see it changes from 2.2 to 1.9. For grand fir, it changes like from 2.25 to 1.9. But for Japanese notch, then they also have variations. So I see maybe there will be for the N value, they are not only have differences between the different species, but they have big variations within 1 disk. So we think why they are changing the shapes from year to another year. So we are guessing maybe this is because about the environment changes from yearly to yearly. So then they also have the influence on the tree shape. And then when we think about that, they have the year interannual variations. Then we make plot the pictures for here. For the picture here, it shows the x-axis. It shows the tree age. That's from the piece to bark. So it's like the tree rings from piece to bark. And this shows the N value. So you can see for Douglas fir and like we can see when it's close to the piece, for the N value, it's like close to 2. So that means, but then later on, when it become bigger and older for the trees, they change the N value increase first and decrease later. And this is similar with the grand fir. But then when we look at about the other species like the silver fir and the cedar spruce, you can see when the younger age, their N value, they have a large fluctuations compared to when they become mature. And this is the same with the Japanese notch. And for the Norway spruce, we can see they are continually changes from yearly to another year. And then how about the K value? The K is equal to the minor semi-axis divided by the major semi-axis. So we can see for Douglas fir and so we can see it increased first and close to 1 and decrease again and increase again. But for Norway spruce and cedar spruce, they are decreasing from piece to bark. So you can see when it's close to piece, they are more like a circle. But when they become older, close to the bark, they are more like an ellipse. And then we try to calculate the basal area increment For here, the two picture for the x-axis, it shows the actual trimming area. It's calculated by the scanner. So it's observed basal area increment. And the y-axis for here, this is we use the ellipse equation to calculate the basal area increment. And for picture 2, this is the trimming area calculated by superellipse equation. So we can see the superellipse equation can fit with the actual basal area increment very good. So I see here, it's much better than we use the ellipse functions to fit to calculate the basal area increment. So then this is our study we have published this year in tree structure and function. And we just try to work on and analyze for 6 discs and 1 disc for 1 conifer species. Then we think about whether we try to work on more discs to see whether they have a common singulars and a common trend. So then we started to work on silver fir, take one species out. And for here, we have worked on 1,090 rings from 5 different sites. Because for here, we also want to see whether they have the site differences for its trimming shapes. For these 5 sites, they are common garden experiment. They were established between the winter of 1963. And so means all the trees, they have same age. And for the different sites, their soil conditions is different. For example, like for site 1010, it have a very nice soil conditions. It's a soil water content is much higher compared to 10.8, compared to 1013. So I see the tree disc, the diameter of the tree disc for 1030 compared to the tree disc come from 1010. So then here, we try to use the superellipse to fit with the tree for this more than 1,000 tree rings of the silver fir. So we can see this is the result of the adjusted root mean square errors for this 28 discs coming from 5 sites. So I see the average MSE of each tree disc is smaller than 0.023, which means that the average absolute deviation between the actual and the predicted tree ring radius did not exceed the 2.3% of the radius of a hypothetical circle with an area equal to the ellipse of the tree rings. So I see when we increase the number and to include a large number of tree rings, we try to test and we found the superellipse function can still fit with the trimming shape of silver fir very good. And we also calculate its K value and also to see the N value of N parameter. So you see the mean estimated K value is ranged from 0.89 to 0.98 with a mean value of 0.95 across all the 1,090 studied tree rings. And the mean value of the N for here, the value of N parameter across all the studied tree rings is 2.04, as is very close to 2. And the mean value of each studied tree disc ranged from 1.93 to 2.15. And we still can see they have a variations within a tree between the tree rings. So we can see for the different colors of the box is from the different sides. So I see within one tree, it has variations for the N value and also for the K value. So we have here for this tree number 6, it has a huge variation for the K value from year to another year. So then we want to see whether they have some size effect or whether they have more variations between the years, but not notice the side effect. So we test, then we found there were no significant differences in the means and the coefficients of variation of N and the K value between the sites. So we found between the 5 sites, they don't have significant differences. But then we start to think whether they have, from the pictures, we can see there are huge differences between the tree rings within a tree disc. So we ask whether they have individual differences. So we found among the 28 studied tree discs, the coefficients of variation of a k-value ranged from 0.98 to 6.29 with an average value of 3. And the coefficients of a variation of n value ranged from 2.49 to 12.03 with a mean value of 5.35. So you see, within a tree, they have variations between the years to year. So we guess this is influenced by the environment. And for here, we take out the two tree discs and to see for this one is the tree number 20, and this is a tree number 4. So tree number 20 has a small is the CV of n value with the value of 2.488, and the tree 4 had the largest NCV with the 12.026. And for the n value of the 43 rings of tree 20, for this tree, ranged from 1.85 to 2.08, and that of tree 4 ranged from 1.64 to 2.47. So we can see that just for this tree, within the one disk, from year to year, we can see they are changing the shape. We randomly take the tree number 4, tree ring number 4, and the tree ring number 25, and tree ring number 36. So you can see this red circle. This is the tree ring number 4. The green circle is the tree ring number 25, and the blue circle, this is the tree ring number 36. And here is the same. The red curve, this is the tree ring 4, and for the blue curve, this is the tree ring 25, and for this blue curve is the tree ring tree ring 36. So I see for this tree, it has a small value of the smallest value of the CV of the n parameter. So I see they are not changing its shape so much from the piece to bark. But for these trees, we can see it has changed the shape. Like we can see this is a number 4 tree ring. This is the number 25. This is the number 36. So for its n value, it is changed from around 2 to higher than 2 and to lower than 2. And we can see these two tree rings, they have a corner. They are changing the corner when they are growing. They are changing from this direction to this direction. But now we don't have so much literatures working about this spiral green for the tree ring disc. And we're thinking about what is the reason why it changes. And the main reason we think is because the wind changes directions. When a strong wind, will influence its growth for its shape. So we'll make a summary for our presentation. The tree ring geometries of the studied conifer disc in most cases do not follow either a circle equation or a typical ellipse equation, but somewhere in between, that is the superellipse equation. Further, most tree ring shapes tend to be bilaterally symmetrical. The simple superellipse equation is sufficient to describe the tree ring boundaries and estimate the basal area increment. The interannual fluctuation of the n value and k value ranged between 1.75 to 2.25 and 0.82 to 1 respectively. This suggests that the shapes of tree rings are not static, but are interannually variable to a large extent as the surrounding environment changes. Because we think about is the changes of the surrounding environment and to influence the tree ring shape. And this study confirmed the potential of the superellipse equation for describing coniferous tree ring shapes as estimating their errors, and is more accurate than ellipse function and also the circle function. But we still have some limitations and we don't know how to solve it. So although the superellipse equation can better describe tree ring shape than the circle ellipse equation, for standing trees in the forest, we more often measure annual increments by taking tree calls, So like because we cannot cut down the trees normally. So if we want to cut down trees, we need to apply. Maybe it will take 2 to 3 years. And for this study, we take the disc from the thinning disc. That is, for the forest, they are doing regular thinning. Every 4 to 5 years, they will thin some co-dominant trees. Then we get a disc to make this study. But normally, if we want to calculate the ring width, the tree ring width, we use the corner to take the tree core out. Or maybe we will measure the diameter at the breast height to calculate the standard tree stalk. And also another question is large numbers of eccentric tree rings are present in the field, like we show you for the original pictures. So we can see the geometrical center of each tree ring is not the piece. They are changing the position all the time from year to year. And it's given that the geometrical centers of tree ring shapes change with the tree age. And the superellipse equation, so we think superellipse equation is more practical for simulating the basal area of a tree disc and rather than tree cores. And we would like to make grateful for the tree disc from the Danish Calm Garden field trials provided by the University of Copenhagen. And thanks a lot for your attention. And thank you very much. And please ask me some questions.